Welcome to ElectronPalooza. I can't even begin to tell you how many things we're going to talk about in terms of electrons today. Our objectives are these. We are going to talk about energy levels, how they are associated with different quantities of energy. They also overlap, which is kind of weird. We're going to talk about some orbitals, these areas where electrons are most likely to be found. Only 2 electrons can fit in any one orbital. We're going to talk about electron configuration. This is just a fancy word for arrangement. We're going to talk about lots of details regarding where electrons can be found in atoms. These rules of arrangement or configuration, there are 3 of them: Aufbau principle, Pauli exclusion principle, and Hund's rule. We're going to talk about the periodic table and how it can be sorted into different blocks based on those orbitals, those areas where electrons are likely to be found. And then we're going to wrap up with a little bit of a look at how electron configuration is related to the number of valence electrons. So to get started, an energy level is a region around the nucleus where electrons are most likely to be moving. This is our Bohr model. We see that we've got one energy level, another energy level. What's interesting about these energy levels and why we call them energy levels is because there are different quantities of energy associated with these different energy levels. The first energy level has less energy than does the second energy level, and the further away from the nucleus we get, the more energy those electrons are going to have. This is showing us how much energy these guys have. Ground level is energy level number 1, energy level number 1. So imagine the nucleus is here, and then here's like that first energy level, and then that next energy level. This is just a tiny little sliver of the whole entire energy level. And you can see that there are different quantities of energies associated with these different energy levels. What's kind of cool, notice the difference in distances between the energy levels. As we get further and further away from the nucleus, these energy levels get closer and closer and closer to each other. They even start to merge into one. A quantum is the amount of energy required to move an electron up one energy level. We're going to do this lab in class. So we're going to take some energy that's going to be absorbed by this electron. It's going to allow that electron to go up to a higher energy level. We call this the excited state. Those electrons have been moved up to higher energy levels. This isn't stable, and so those electrons are going to release that energy and go back down to their usual spot. That lowest possible energy level is known as ground state. So a quick review here of where electrons even are. Early atomic theorists, Rutherford, said that those electrons are orbiting the nucleus. Bohr made it a little bit better and said they're orbiting in different levels, those different energy levels. Then Schrödinger said you are all wrong. It's not paths that they follow like planets around a sun, but instead we have orbitals, not orbits, but orbitals, which are fuzzy clouds where we're more likely to find an electron. And so there are really more of these spaces where electrons are moving, and those electrons can definitely jump out, but then they'll go back. The probability of finding an electron here is high. Different energy levels, energy level number 1, we're going to find electrons more here than anywhere else. Energy level number 2, they're going to be here. Energy level number 3, they're going to be here. And so different energy levels are going to have different orbitals because of those different quantities of energy. And because those different energy levels have different quantities of energy, we actually give them special energy numbers, and it's super easy. So energy level number 1 is called n equals 1, and we call that the principal quantum number, just that energy level. Energy level number 2, you can probably guess, is 2, and n equals 3 is for energy level number 3. N equals 4, energy level number 4. The higher this principal quantum number, the greater the amount of energy those electrons have. Here's where things start to get a little bit crazy. Different energy levels have different sub-levels. So you can imagine there's like an apartment building, and on the first floor, energy level number 1, there's only one apartment. There's only one apartment in energy level number 1. In energy level number 2, kind of like the second floor of an apartment building, there are actually 2 apartments, 2 sublevels. Energy level number 3, The third floor of the apartment building actually has 1, 2, 3 different apartments. There are 3 sublevels in energy level number 3. And I bet you guessed the pattern. In energy level number 4, there are 4 sublevels. Imagine that on the 4th floor of this apartment building, there are 1, 2, 3, 4 apartments. But they're not all the same. So we have some different kinds of sublevels in this apartment. Our sublevels are designated by letters. So these different kinds of sublevels are S's, P's, D's, and F's. Remember in our apartment building analogy, we had those floors. Energy level number 1, that first floor only has 1 apartment. We're going to call that the S. Energy level number 2, that second floor has 2 apartments. We're going to call those S and P. S and P. The third energy level, that third floor of the apartment building, adds another apartment. We have S and P, and now we're going to add a D. S and P and D. Energy level number 4, or the 4th floor of our apartment building, we have 1, 2, 3, 4, 4S, 4P, 4D, and now we're going to add F for F. What we're looking at is just getting super specific about where even are these electrons on the atom. Imagine this is like an address or a zip code for where electrons are, and they might be here, or they might be here, or they might be here. And this method is just helping us be super specific about where electrons are in the atoms. What's super cool about these different kinds of sublevels is they come in different shapes. S sublevels, there's 1S and 2S and 3S on up, are all spherically shaped. P's are dumbbells, D's are clover leaves, and F are complex. We don't even know how to call those shapes. We just call them complex. Here are some pictures. Here are those S orbitals that are spherically shaped. Here are our P orbitals. They are shaped like dumbbells. Here's D. They are shaped like clover leaves, except for this guy that's like a dumbbell with a donut. And then these are our F orbitals. They are complex because we don't know how to call these shapes because they're very complex. All right, so these different shapes also come with some numbers, and then this orientation of the orbital in space. So you know how in math we have like the x-axis and the y-axis, and if we're talking about 3 dimensions, then we have the z-axis that goes in and out of the paper. So that's what we're talking about with these different orientations of orbitals. So our P guys, these 3 P dumbbell orbitals, can go up and down like they're on the y-axis, they can go back and forth like they're on the x, or they can go in and out of the paper like they're on the z. And so that's what this is just saying, is that we can have these different orientations. So the more orbitals we have, the more orientations we have, and we can add kind of like zip code numbers. We can add numbers to distinguish what orientation these different clouds have. Again, we're still talking about where even are the electrons. So this is one of those clouds that the electrons are flying around in, and we can just use these numbers to help us be super specific about where the electrons are. That's all this is about, is where even are those electrons. Again, it's kind of like a zip code. It's kind of like talking about us in Denton. So we are in the city of Denton. More specifically, we're at DHS. More specifically, we're in the science wing. More specifically than that, we're in classroom C203. And there's 30 of us students in C203 most days. Similar to that is our sulfur atom. In the sulfur atom, kind of like in the city of Denton, we can get more specific and we can talk about energy level number 3, like we can talk about that building DHS. We can get more specific than energy level number 3 and we can talk about the P sublevel. We can get more specific and say not just the P sublevel, but the P sublevel that's on the y-axis. And then we can talk about the 2 electrons that you can find in that y-oriented 3p sublevel in the 3rd energy level of a sulfur atom. It's just about being super specific about where even are these electrons. All right, so when we kind of make these zip code-like electron configurations or arrangements, there are 3 rules that we have to follow. The first one is the Aufbau principle. This one's easy. Electrons are always going to go to the lowest energy level available first. They're not going to jump up to energy level number 7 unless 1, 2, 3, 4, 5, and 6 are all full. Pauli exclusion principle number 2. We can only fit 2 electrons in each orbital. There is only space for 2 electrons in each orbital, and because electrons have the same charge, they repel each other, they're going to have opposite spins, and we show those spins with oppositely directed arrows. And sometimes we get lazy, we don't even draw a whole arrow, we just draw like half an arrow, so an up and a down. We can also add another one of those numbers for the spin, plus half or minus half. Don't worry so much about the halves, we're just going to use the arrows. All right, the third rule is really weird and doesn't make sense until we start actually doing some electron configurations, but a little bit of a preview. If we have orbitals with equal amounts of energy, like there are 3 different p orbitals, they all have equal energy. We're only going to put 1 electron in each orbital, even though there's space for 2. We're going to make sure that each of those p orbitals has 1, and then we'll add the second one with that opposite spin later. All right, so let's practice a little bit of electron configuration. The rules make a whole lot more sense if we're practicing. Hydrogen. Hydrogen has 1 electron, assuming that it's a neutral atom and not an ion. That 1 electron is going to go into the lowest energy level first. 1 is the lowest possible energy level, and energy level number 1 only has an s orbital. So I'm going to draw an arrow. That arrow is representing the 1 electron in hydrogen. And that's it. That's the whole entire electron configuration. I have 1 electron with an up spin in the 1s orbital. Helium has 2 electrons. I'm going to again start lowest energy level first because that's what Aufbau principle tells me. And I'm going to have an up spin and then a down spin on these electrons. They spin in opposite directions because they repel each other because they're both negatively charged. And we can fit them closer to each other if they have opposite spins. That is that Pauli exclusion principle. Pauli exclusion says only 2 electrons can fit in any one orbital, and this is representing one of those orbitals, one of those clouds where we can find electrons. Pauli exclusion principle says up arrow, down arrow to show those electrons in opposite spins. All right, lithium. Lithium is here. It has 3 electrons. We're going to show the 3 electrons with arrows up, down. Again, sometimes we get lazy and we only draw half an arrowhead. So there's 1 electron. Here's 2 electrons. Electron number 3 cannot fit here because Pauli says only 2 electrons in any one orbital. So the next one's going to have to go here in the 2s. So I have 2 in the 1s and 1 in the 2s. Beryllium. Beryllium's here. 4 electrons. We're going to fill up that 1s with an up and a down. Those arrows are showing the electrons spinning in opposite directions. And then in the 2s, we're going to also have 2 electrons also spinning opposite. I see those 1, 2, 3, 4 electrons of beryllium. Let's do carbon. We're going to skip boron and go all the way to carbon. Carbon has 6 total electrons. 6 electrons in carbon. I'm going to go up, down, there's 1, 2, 3, 4, there's 5, 6. Here's where Hund's rule comes into place. That weird one about you can only put 1 electron in each orbital until everybody has 1, and then you can add the second. So here's what we are not going to do. We are not going to go, here's 2 electrons, here's 2, that's 4, 5, 6. That is not right. Instead, what we're going to do is take that last electron and we're going to spread it out over here because all of these guys in the 2p have equal amounts of energy. And so I'm going to put 1 here and 1 here because I have space. I have lots of room to spread out in the 2p. This is kind of like the 2p orbital that's on the x-axis. This is the 2p orbital that's on the z. Ooh, that's y, and then the z. So these guys are all oriented in different space, planes of space. So this is our electron configuration for carbon. We're going to spread these guys out because we can. Let's do oxygen. Oxygen has 8 electrons. 8 electrons. I'm going to show them with 1, 2, 3, 4, 5, 6, 7. I am not going to cross this line because that's 3s. That is more energy than 2p. So now I'm going to go back and add the second electron right here in that first chunk of the 2p. So this is the electron configuration for oxygen. I have 1, 2, 3, 4, 5, 6, 7, 8 electrons, but I spread them out until I didn't have space, and then I went back. All right, let's do neon. Neon has 10 electrons. Neon is here with 10 electrons. I have up, down, there's 1, 2, up, down, there's 3, 4, up, 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 arrows, there's 5, 6, 7, and I'm going to go back 8, 9, 10. This is our electron configuration for neon. What about sodium? Sodium has 11 electrons. 11 electrons. Up, down, there's 1, 2, 3, 4, 5, 6, 7. Go back 8, 9, 10. I have now filled the 2p orbitals. I can go one more, 3s up. There's 1 up for the 3s orbital. Good. All right. So here's where things get kind of wonky. This Aufbau diagram is showing us increasing energy going up. 1s has the lowest energy, 2s has the next, and then 2p. That makes sense. 3s, 3p, 4s. Wait, what just happened? 3d? 3D? How does 3D have more energy than 4s? It's because, remember a long time ago I said as those energy levels get further away from the nucleus, they start to get closer and closer and closer to each other? Well, they actually start to get so close to each other that they start to overlap. And that's what's happened here. So 4s actually has less energy than does 3D. And after 3D, we have 4p and then 5s, and then we go back to 4D, and then 5p, and then 6s. And are you ready for this? We go from 6s to 4f to 5d to 3p. Oh, that is not a 3. That's a 6. Whoa! Crazy sauce, right? I will not make you memorize this. I will always give you one of these Aufbau diagrams when we do this. So do not panic. Do not panic. You don't have to memorize this, but you need to know that we're always going to work up the energy levels. All right, let's practice a little bit more. So let's look at lithium again. Remember that lithium was up, down, up because it has those 3 electrons. Now I'm going to start adding this electron configuration notation. So we have 2 electrons in the 1s orbital, 1 electron in the 2s orbital. These exponents are telling us how many electrons are in each one of these orbitals. Beryllium, Be, beryllium is here with 4 electrons. 4 electrons in beryllium. Remember that we start in the 1s, we go up, down, and then in the 2s we have 3, 4, up, down. So our electron configuration notation is going to be 1s2, 2s2, because I have 2 electrons in the 1s orbital, and 2 electrons in the 2s orbital. Let's do boron. Boron's over here with 5 electrons. We're going to go up, down, up, down, up. 1, 2, 3, 4, 5 electrons. 1s2, 2 electrons in the 1s, 2s2, 2 electrons in the 2s, 2p1, 1 electron in the 2p sublevel. Boron's big B. All right, carbon is 6. Big letter C. We're going to go up, down, there's 1, 2, up, down, there's 3, 4. Hund's rule, remember, we're going to go 5, 6. We're going to spread those guys out. And that doesn't even make a difference when we do this notation stuff. Carbon is going to be 1s2, 2 electrons in the 1s, 2s2, 2 electrons in the 2s, and 2 total electrons in 2p. We're just going to write 2p2. Even though they're spread out, they're still just 2 electrons in the 2p2. All right, let's practice a little bit more. Iron. Iron is here. 26 electrons. We always start in the Aufbau diagram at the bottom. Up, down, 1, 2, 3, 4, 5, 6, 7. Remember Hund's rule, we spread them out until they've each got 1, and then we go back and add more. So there's 2, 4, 6, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We need to get to 26. 21, 22, 23, 24, 25, 26. So this is the electron configuration for iron. To write it out, we're going to do 2 in the 1s, 1s2, 2 in the 2s, 2s2, 2, 4, 6 in the 2p, 2p6, 2 in the 3s, 3s2, 6 in the 3p, 3p6, 2 and 4s, 4s2, and then we do the weird thing where we go backwards to the 3d. 2, 3, 4, 5, 6, 3d, 6. This is the electron configuration for iron. Good, good. Let's do zinc. Zinc is here with 30 electrons. Do I need to erase all of this and start over? No, I'm going to keep going. This was already 26 electrons. I just need to add 4 more to get to zinc. So here's electron number 27, 28, 29, 30. So this is 30 electrons for zinc. Same idea, we're going to start with that 1s2, 1s2, 2s2, 2s2, 2p6, 2p6, 3s2, 3p6, 4s2, 3d, 2, 4, 6, 8, 10, 3d, 10. That's zinc. Good. All right, let's practice some more. Okay, so argon. Argon has 18 electrons. It's right here. We're going to go up, down, 1, 2, up, down, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, up, down, 13, 14, 15, 16, 17, 18, 18 electrons. In argon, we end at 3p. I'm going to write the electron configuration notation. 1s2, 2s2, 2p, 2, 4, 6 in the 2p, 2p6, 3s2, 3s2, 3p6, 3p6 in the 3p sublevel. All right, so let's do potassium. Potassium is 1 more than argon, so really I can keep argon, just add 1 more. Now I have potassium. So basically potassium is all of argon plus 1 more. 1s2, 2s2, 2p6, 3s2, 3p6, same as argon, and then I'm going to add 4s1. Wouldn't it be nice if we had a shortcut where we could just say that potassium is 1 more than argon? We do! We have noble gas configuration. This only works with noble gases. Only works with noble gases. But you can take the noble gas that comes in the periodic table before an element, find its match, and then you can write, instead of all of this, you can say all of this is the same as argon. So you can put argon like this in those brackets, and then just what's extra, 4s1. So potassium can also be written as argon and 4s1. Good. Cesium, oh my gosh, cesium's way down here. Cesium has so many electrons. We do not have to write the whole entire cesium. Instead, I can just go backwards through the periodic table. What comes before cesium? Xenon does. Xenon is the noble gas that comes before cesium. So I'm going to put xenon in those brackets. What comes after xenon? 1 whole electron. And I just totally covered up something that I wanted us to see. 1 whole electron. We're always going to start in the S. We always start in the S, right? So we always have S first. So I'm going to have an S, and there's only 1 electron, so there's a 1. But what energy level should I do? 1, 2, 3, 4, 5, 6? Yes, 6, because look right there, there's a 6. So the noble gas configuration, or condensed shortcut configuration for cesium, is all the electrons that xenon has plus 6s1. 1 electron in the s orbital of the 6th energy level. All right, what's wrong with this picture? Take a look. Lithium has 3 electrons, 1s2, 3s1. Crazy sauce. How can that happen? Remember a really long time ago, in this slideshow where I said we can add some energy to electrons and they can jump to higher energy levels, this is what happened. So this we would call the excited state, because the electron that ought to be here gained some energy and jumped way up there. So this is weird, but possible, but weird. All right. So now I'm going to talk a little bit about how these orbitals, these shapes, relate to the periodic table. So our s orbitals, remember, are spherically shaped. The first energy level, period number 1, only has an s orbital. All of these guys have only s. The p sublevels are here. The second energy level has s first and then p. These elements only have electrons in the 2s orbitals. These guys over here have electrons in the 2p. Third energy level. These guys are s. These guys are p. And remember how we have that weird overlappy thing? This is the 3d. Crazy sauce, right? So these D clover leaves and the dumbbell with the donut, that's these guys right here. And then the F's are way down here. So all of the elements in these 2 rows have their valence electrons in these F orbitals. All right, so we can kind of think about the same idea, but instead in these blocks. So I'm going to call this chunk of the periodic table the S block, and you can imagine that helium is actually over here, also in the S block. This is the P block, here is the D block, and down here is the F block. I definitely would annotate your periodic table with this. You have S, you have P, you have D, and way down here is F. This is showing us that weird overlappy thing. The magic of this is we can use these ideas to kind of predict where elements are in the periodic table in terms of their electron configuration. So again, here is my s orbital. I'm going to push helium over here. So here's S block. Here's that P block. D is here in the middle, and then F is down here. I have energy level number 1, 2, 3, 4, 5, 6, 7. We do that weird overlappy thing. So even though this looks like 4, it's actually 3D, 4D, 5D, because they overlap. Transition metals are weird, and this is one of the reasons why. They have those overlapping energy levels. And then the F actually starts at 4F, and this is 5F. Again, because of that crazy overlappy stuff. All right, so let's say I want to pick lithium. So lithium is here. This is the S block. Lithium is the first guy in the S block, energy level number 2. Lithium's electron configuration is 1s2, 2s1. If I look at that last guy, 2s1, 2s block, the first guy in the S block, 2s1. If I looked perhaps at strontium, strontium is right here. It has a big, long electron configuration, but it's going to end in 5. S block, 1, 2. S2 will be the end of strontium's electron configuration. If I look here at nitrogen, nitrogen is here. It's in the P block. It's in the second energy level. Energy level number 2 is here. P block 1, 2, 3, 4, 5, 6. Nitrogen's very last piece of its electron configuration is going to be 2p3. 2, second energy level, P block, 1, 2, 3 guys over, 2p3. If I look at, let's look at xenon. Xenon is here in energy level number 5. Energy level number 5. All the way over, here's xenon. Xenon's last piece of its electron configuration is going to end in 5. 5. p block, p, 1, 2, 3, 4, 5, 6. 5p6 will be the very end of xenon's electron configuration. Let's say that we want to look at zinc. Zinc is here. Zinc is going to end not in 4, but in 3 because of that weird overlappy thing. Zinc is going to end in 3d. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3d10 will be the last electron in zinc's electron configuration. All right. So we talked a lot about those last electrons. Those last electrons are valence electrons. They are super important. They are the ones in the outermost energy level. Oxygen has 1, 2, 3, 4, 5, 6. Why we care so much about valence electrons, these are the guys that are involved in chemical bonds. Makes them super, super important. And elements in the same group on the periodic table have similar properties because they have those same numbers of valence electrons. And our A numbers tell us how many valence electrons these guys have. Transition metals are weird because of the overlapping stuff. And so they're B's, and so we don't really talk about them. Not quite as much, at least not this year in honors chem. So beryllium has 2 valence electrons, fluorine has 7 valence electrons, argon has 8. Helium is an 8, but helium's weird. It actually only has 2 valence electrons because it's an energy level number 1, right? Good. So looking at Lewis dot structures, remember this is how we show the number of valence electrons. Electrons, I can spell. Hydrogen has 1, lithium has 1, sodium has 1, potassium has 1 because they are all alkali metals. Beryllium has 2, magnesium has 2, calcium has 2 because they're all alkaline earth metals. These guys are in the 3A. They have 1, 2, 3. Aluminum has 1, 2, 3. Carbon's in 4A. He has 1, 2, 3, 4. Nitrogen is in 5A. 1, 2, 3, 4, 5. All of these guys will have 6. All of these guys will have 7. All of these guys will have 8. Helium has 2 because it's in that first energy level and it only has space for 2. So why I reviewed those valence electrons and Lewis dot structures here in our electron configuration video is this. So looking at hydrogen's 1 valence electron, notice the last number there. Cool beans, right? 1 valence electron, the last number is 1. 2 valence electrons in helium, that's them 2. 1 valence electron, there's lithium's 1 in the 2s orbital. Beryllium's 2 are here. 3 valence electrons in boron. Boron's in energy level number 2, so I only care about the 2s. I care about the S's and the P's. These are all considered valence electrons. So 2 S's plus 1 P means 3 valence electrons. Again, count up how many electrons in S and P in the highest energy level. For carbon, it's 2. 2 plus 2 makes 4 valence electrons. We only care about that highest energy level. 2 and 2 is the outermost energy level number 2. 2 plus 3 makes 5 valence electrons. I'm going to skip down to neon. Again, we're only looking at energy level number 2 because 1 is not valence. Energy level number 2 is the outermost energy level for neon. And if I add up S and P, 2 plus 6 makes 8. 8 valence electrons for neon. Cool beans, right? And we did it! I know this was a little bit of a long video, but I am so proud of you for hanging on till the very end. We met all of our objectives. We talked about energy levels and how they are associated with different quantities of energy. Closer to the nucleus has less energy, further away has more. But they also overlap because the further away from the nucleus we get, the closer they get to each other. That weird overlappy thing, we go from 3p to 4s back to 3. 3d has more energy than 4s. 4s has less than 3d because this is where that overlapping stuff starts to happen. Orbitals are areas where electrons are most likely to be found. Only 2 electrons can fit in any one orbital. Pauli exclusion principle says so. Electron configuration follows those 3 rules. Pauli exclusion principle. Aufbau, we always start at the lowest energy level first. Hund's rule. If you have something like the p's and there are 3 different orbitals in p because we have X, Y, and Z, we're going to go up, 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 and then we're going to go back, down, down, down. That's Hund's rule. The periodic table is sorted into those blocks based on orbitals. So periodic table kind of looks like this. That's a very, very sad rendering of the periodic table. This is S, this is P, this is D, and this is F. Those are the blocks of the periodic table. And last but not least, we can look at those electron configurations to figure out valence electrons. If I've got something like carbons 1s2, 2s2, 2p2, if I look just at the last energy level, which is energy level number 2, and I add up the s's and the p's, 2 plus 2 makes 4 valence electrons. Good work, my friends.